Welcome to Talk Tensors.
Glad to be here for this one.
Yeah, today we're dissecting a structural paradigm shift in computer vision. Specifically, we're doing a deep dive into the 2017 paper, Feature Pyramid Networks for Object Detection,
by Songyi Lin and the team at FAIR, Facebook AI Research, and Cornell.
Right, and this arrived at a time when the field was, wrestling with this really brutal hardware versus accuracy bottleneck.
Oh, absolutely brutal.
So if you are a grad student dissecting architectures for a thesis or an industry researcher looking for historical context, this deep dive is engineered for you.
We're not doing a superficial skim today.
Exactly. We're treating this like a faculty lounge post-mortem. Sharp, highly technical, and strictly focused on the architectural mechanics.
And I think the timing of this paper in the historical literature really can't be overstated.
Right, 2017.
Yeah. By 2017, the deep learning community had effectively conquered image classification. We had architectures like ResNet, which Kaming He, who is actually a co-author on this paper, introduced just 2 years prior.
Which was a massive deal on its own.
Exactly. We had models that could categorize an image of a dog with basically superhuman accuracy.
But classification is just what is in this image.
Right. The frontier had shifted to object detection. Not just what is it, but exactly which pixels does this object occupy and how many of them are there.
And doing that across vastly different scales was computationally crippling at the time.
It was a nightmare. Which brings us to the core breakthrough we're unpacking today.
The thesis.
Right. The researchers figured out how to naturally leverage the inherent pyramidal shape of a deep convolutional network to construct highly semantic, multi-scale feature pyramid.
And crucially, they did this at almost zero extra computational cost.
Yeah, they basically weaponized the network's own depth. They turned what was traditionally a byproduct of convolutional downsampling into a primary architectural feature.
Because before FPN, which is what we'll call the feature pyramid network today, designing a system to detect both a massive screen-filling object and a tiny distant object in the same image required you to accept some really unfortunate compromises.
You basically had two bad choices. You either sacrificed inference speed by evaluating the image multiple times at different scale,
Which was incredibly slow.
Or you sacrifice recall on small objects by only looking at the image once through a deep, coarse filter.
Right. And FPN introduced a routing mechanism that shattered that dichotomy. A top-down pathway with lateral connections.
Which sounds simple, but we'll see why it was so revolutionary.
So here's our roadmap for the deep dive. We'll start by contextualizing the breakthrough. We'll examine the constraints of the pre-deep learning era and early ComNets.
The era of compromise.
Exactly. Then we'll execute a component-by-component teardown of the FPN methodology, the exact tensor operations in the bottom-up, top-down, and lateral pathways.
And how they integrated it into the region proposal network and Fast R-CNN.
We'll pay special attention to the mathematical heuristics for region of interest assignment there. Then we'll analyze the MS COCO's benchmark results, dissect the ablation studies, and look at its lasting legacy.
And we'll pitch some novel applications at the end.
Yes, the novel notion segment. So by the end of this deep dive, you will fundamentally understand why modern object detection looks the way it does.
And how a remarkably simple routing trick solved the small object problem that plagued early deep learning models.
All right, let's jump into the pre-deep learning dark ages. The white whale of computer vision has always been scale and variance.
Yeah, for decades, because if you train a system to recognize a car that takes up 500 by 500 pixels, that same system will fundamentally fail to recognize the identical car when it's driving in the background and only occupies 30 by 30 pixels.
The raw pixel gradients are entirely different.
Completely different.
So in the era of hand-engineered features, I'm talking about SIFT, the scale invariant feature transform, and HOG, histograms of oriented gradients.
Right, the classics.
The brute force solution back then was the featurized image pyramid. The algorithm itself wasn't natively scale invariant, so researchers had to physically manipulate the input data to artificially create that invariance.
The standard protocol was literally taking the high-resolution input image and repeatedly downsampling it.
Usually by applying a Gaussian blur first to prevent aliasing, right?
Yeah, blur. then subsample. You'd build a massive literal pyramid of the same image at different resolutions. And then, and this is the painful part, you would pass your HOG or SICT extractor over every single level of that pyramid independently.
Which is just a staggering amount of computational redundancy.
Oh, it was an operational nightmare. If you were running a deformable part-based model, a DPM, you were evaluating a root filter for the whole object at a coarse resolution and part filters at twice that resolution.
Like looking for the wheels of a car specifically.
Exactly. And the paper notes that DPMs required dense scale sampling, sometimes calculating features at 10 different scales per octave.
And just to clarify for everyone, an octave in this context represents a halving of the spatial dimensions.
Right. So generating 10 intermediate feature maps just to get from a 512 by 512 image down to a 256 by 256 image.
That means you are forcing the CPU to recompute localized gradients over and over again on virtually identical pixel neighborhoods.
It was incredibly slow, but honestly, it yielded the highest accuracy on datasets like Pascal VOC at the time. It was the best we had.
Until the paradigm shifted.
Violently shifted around 2012 to 2014 with modern ConvNets, AlexNet, VGG, the early R-CNN models.
We finally abandoned hand-engineered features for learned representations.
And accuracy skyrocketed because the networks were learning these incredibly deep, high-level semantics.
But the scale variance problem didn't just magically disappear.
No, it didn't. Early deep learning detectors like Overfeet, they still tried to use those featurized image pyramids at test time.
Right, running the entire deep condet as a sliding window over multiple scales of the input image.
And they immediately slammed into a hardware wall. You have to remember the physical constraints of the era we're talking about.
The GPUs.
Yeah, we were operating on GPUs like the NVIDIA K40 or the Titan X. You had maybe 12 gigabytes of VRAM.
Max.
Right. So running a deep multi-layer ConvNet independently on a dense image pyramid was completely memory infeasible for end-to-end training.
And even at inference time, running an image pyramid increased processing latency by a factor of 4 compared to processing a single scale.
You just can't deploy a model with the multi-second inference time into a self-driving car. It's useless.
So the field was forced into a tactical retreat, essentially. To achieve practical inference speeds, the architects of Fast R-CNN and Faster R-CNN opted for single-scale features.
They traded multi-scale robustness for speed. They passed the input through the network exactly once, extracting a single feature map from one of the deepest layers of the content.
Which was a necessary compromise, but it introduced a severe vulnerability, the missing small objects problem.
Because of how convolutional neural networks actually work, as a tensor passes through the layers, it's repeatedly subjected to convolution with stride or spatial pooling operations.
So the receptive field of the neurons expands drastically.
Exactly. In the early layers, a single neuron might only compute activations based on a 3x3 pixel neighborhood in the original image. It's basically an edge detector.
But by the time you reach the final convolutional layers, a single neuron's receptive field might cover a massive 1,000 by 1,000 pixel area.
The depth of the tensor, the channel dimension, increases dramatically to store all that complex semantic information, but the spatial resolution is decimated.
Right. The result is a feature map that is semantically profound, but spatially coarse.
The final layer of a ResNet knows exactly what a bicycle looks like. It understands the geometric relationship between circles, metal tubes, rubber textures.
But if you ask that layer exactly where the bicycle's tire ends and the pavement begins,
it has no idea. The spatial coordinates have been pulled away.
So if you have a high-resolution image with a massive bus in the foreground and a tiny pedestrian in the background, the single-scale Fast R-CNN easily detects the bus.
The deep feature map has the semantic depth to classify it.
But the pedestrian gets mathematically erased. It's just lost in the low-resolution feature maps of the final layers.
Right. It might be smaller than a single cell in the feature map grid by that point. Researchers knew this was an issue immediately, which led to attempts like the single shot detector or SSD.
The SSD is a really critical stepping stone here, because they realized a standard ConvNet is already a feature pyramid in a way.
It is. The early layers are wide and spatially expansive, and the deeper layers are narrow and spatially compressed.
So instead of predicting objects solely from the final layer, SSD attached classification and regression heads to multiple layers throughout the network's forward pass.
It's a theoretically sound approach, but it missed a massive opportunity because of a misunderstanding of semantic depth.
Right. They attempted to predict small objects using the early layers and large objects using the deeper layers.
But the early layers of a convnet conv1 or conv2 are functionally just Gabor filters. They respond to directional gradients, contrasting colors, sharp corners.
They have zero high-level semantic understanding.
Exactly. You can't attach a classification head to an edge detector and expect it to confidently classify a dog. The feature representation is just too weak.
So what did SSD do to fix that?
They basically threw the baby out with the bathwater. To avoid using those weak, low-level features, they just discarded the foundational high-resolution layers entirely.
They started building their pyramid from the middle layers onward.
Specifically starting from the conv4 layer in a VGG16 backbone, and then they appended several artificially constructed, increasingly coarse layers to the end of the network.
By discarding those early layers, they threw away the exact data required to precisely localize small objects. They traded a scale problem for a semantic problem.
And benchmark recall on small objects remained frustratingly low.
Which brings us to the aha moment of the feature pyramid network. The creators realized you don't have to throw away the high-resolution maps.
You just have to fix their weak semantics.
It's like a corporate structure analogy. You have the bottom-up pathway, which is the ground floor, high resolution, lots of local detail, but no big-picture strategy.
And the top-down pathway is the executive suite. Low resolution, highly semantic. It knows what a cat is, but it doesn't know exactly which pixel the cat's ear is on.
And FPN forces them to talk to each other.
Yeah.
Let's dissect this methodology. The FPN architecture is a two-way street. Component one, the bottom-up pathway.
This is just the standard feed-forward computation of a backbone convnet. In this research, they specifically use ResNet.
As an image propagates through a ResNet, it's processed in distinct stages.
A stage being a contiguous sequence of residual blocks that output feature maps of the exact same spatial dimensions.
And between each stage, there's a subsampling operation.
Right. Having the spatial width and height, and usually doubling the channel depth, the researchers decided to extract one reference feature map from each stage.
Specifically the output of the final residual block in each stage.
Because that deepest layer in a stage has undergone the maximum amount of nonlinear computation for that specific spatial resolution. It has the richest features before the destructive subsampling happens.
So they denote these layers as C2, C3, C4, and C5, corresponding to strides of 4, 8, 16, and 32 pixels relative to the input image.
Right. So a stride of 32 for C5 means a single activation there represents a 32 by 32 pixel region in the original image. Very coarse localization.
And listeners might notice we started at C2. We ignored C1, the output of the first convolutional layer.
Which seems counterintuitive if you want high resolution for small objects.
Exactly. Why exclude the highest resolution layer?
Pure computational pragmatism. C1 has a stride of 2. It's massive, half the size of the original input. Including it and attaching dense anchor heads to it would incur a massive memory footprint.
And severe inference latency.
For only a very marginal gain in semantic representation, they optimize for practical deployment, bounding it between stride 4 and stride 32.
Okay, so that's the bottom of scaffolding. The deeper we go, the richer the semantics, but the poorer the spatial resolution. Now, component 2, the top-down pathway.
The goal here is to hallucinate higher resolution features by upsampling the spatially coarse but semantically dominant feature maps from the top.
Starting at the very top, C5. It has the strongest semantics. They upsample the spatially coarser map by a factor of 2.
And the technique here is critical. They didn't use learned deconvolution or transpose convolutions. They used simple nearest neighbor upsampling.
Right. Why is that distinction so important?
Because it achieves spatial expansion without introducing a single trainable parameter. It completely avoids the checkerboard artifacts you get with transpose convolutions.
It's purely deterministic.
Yeah. If you have a 2x2 matrix, nearest neighbor upsampling by a factor of 2 just duplicates each scalar value into a 2x2 block, so you get a 4x4 matrix. 0 compute required.
But the trade-off is that the resulting upsample tensor is highly aliased.
It's blocky, fundamentally imprecise. You now have a map that is twice as large spatially, matching the C4 layer below it, and it contains top-tier semantic understanding.
But it lacks localized sharpness.
Exactly.
Which brings us to component 3, The lateral connections. This is the secret sauce, the communication protocol that merges the bottom-up pathway with the top-down pathway.
You take that newly upsampled C5 tensor, and you merge it with the corresponding bottom-up C4 tensor of the exact same spatial size.
But you can't just mash them together. There's a dimensionality mismatch.
Right. The bottom-up C4 tensor from ResNet has 124 channels, but the top-down tensor needs to be standardized. You can't do element-wise addition on tensors with different channel dimensions.
So they apply a one-by-one convolution to the bottom-up feature map.
A one-by-one conv acts as a linear projection across the channel dimension. It evaluates a single spatial location and computes a linear combination of all the depth channels at that coordinate.
And outputs a new specified number of channels. In this case, exactly 256.
So C4 is projected down to 256 channels. The upsampled top-down tensor also has 256 channels. Now they perfectly align.
And they are merged via simple element-wise addition.
Which is such an elegant choice. During backpropagation, an element-wise addition operates as a perfect gradient distributor.
The error signal just flows backward, and the addition node copies the gradient, passing it equally to both the top-down pathway and the lateral bottom-up pathway.
It prevents the vanishing gradient problem and ensures both branches are optimized simultaneously. Same mathematical philosophy as the residual blocks in ResNet itself.
So you're enriching the highly localized, high-resolution activations of the bottom-up map with the profound semantic context of the top-down map.
You're taking the precise edge coordinates from C4 and painting them with the semantic class understanding from C5.
I love that visual. And then there's one final polish, a 3x3 convolution applied to this merged map.
Mandatory step. The nearest neighbor upsampling introduces blocky artifacts, high-frequency noise. The prediction heads would misinterpret those grid lines as physical edges in the image.
So the 3x3 convolution acts as a localized spatial low-pass filter, blurring the artifacts.
Smoothing the tensor into the final feature map for that specific scale.
And this generates the new pyramid levels, P2, P3, P4, and P5. This process is iterated sequentially all the way down.
Upsample, add smooth. Upsample, add smooth.
And the most vital takeaway is the enforced uniformity. Every single level of the P pyramid now has exactly 256 channels.
And every single level is semantically rich. The semantic gap is bridged.
And the authors noted they tried more complex connection modules, right? Like multi-layer residual blocks for the laterals.
They did. And they found only marginal gains. The brilliance really is in the simplicity. No non-linearities in the extra layers, just one-by-one comms, nearest neighbor upsampling, and addition.
State-of-the-art multi-scale representation with virtually zero extra computational overhead.
But building the pyramid is only half the battle. You need a detection head capable of deciphering it.
Which transitions us to the integration phase, supercharging the region proposal network and fast R-CNN. Let's look at RPN first.
So RPN normally uses a single-scale feature map and dense 3x3 sliding windows with multiple anchor scales.
Because it only had one map, it had to use anchors of drastically different sizes at every single location. A 128 anchor, a 256 anchor, a 512 anchor, all centered on the exact same pixel.
A very dense, highly overlapping search grid. But with FPN, we have a spatial hierarchy from P2 to P5.
So the shift is that the 3x3 convolutional head is attached to every level of the pyramid.
Identical copies of the head. It's scanning across the high-resolution P2 grid while simultaneously scanning across the coarse P5 grid.
Which eliminates the need for multi-scale anchors at a single level. They optimize the anchor assignment by assigning a specific single-scale anchor to each level.
A very logical division of labor. You don't search for a massive 512 pixel object on the high-resolution P2 map. The object is bigger than the localized receptive field.
And you don't look for tiny objects on deep maps. So P2 gets 32 squared pixels, P3 gets 64 squared, P4 handles 128 squared, and P5 handles 256 squared.
And they also introduced a new P6 level exclusively for the RPN.
Just a stride 2 subsampling of P5.
Exactly, generated by a one-by-one convolution. And P6 handles the massive anchors of 512 squared pixels. At every level, they maintain 3 aspect ratios. 1:2, 1:1, and 2:1.
Giving 15 distinct anchor configurations across the pyramid. But the most profound engineering decision here is the parameter sharing.
This is huge. The parameters of the prediction heads are shared across all pyramid levels.
So the exact same weight matrix evaluating the dense P2 map is evaluating the deeply abstracted P6 map.
And the fact that this works, that it yields equivalent or superior accuracy, is a monumental validation of the FPN architecture.
Because if they had different semantic depths, a shared weight matrix would completely fail.
It proves mathematically that the top-down pathway successfully forced all levels to converge on a shared semantic representation space. It's the ultimate proof of translation invariance across scale.
All right, so RPN generates the region proposals. Then they pass to the fast R-CNN classification and bounding box regression head. This requires region of interest, or ROI, pooling,
which is a quantization operation, taking a continuous floating point bounding box proposal and projecting it onto the discrete integer-based grid of a feature map.
Usually dividing it into a fixed 7x7 spatial grid and performing max pooling within each bin.
So you always get a fixed 7x7x2 56 tensor regardless of the proposal's original aspect ratio.
But with standard fast R-CNN, there was only one feature map. With FPN, you have P2, P3, P4, and P5. If you have a proposal, which level do you pull the ROI from?
Right. If you pull a massive proposal from P2, the 7x7 grid misses massive amounts of internal semantic context. If you pull a tiny proposal from P5, the object is obliterated.
So they solved this with a heuristic assignment equation. And I want to walk through the math here because it's foundational. The equation is K equals the floor of K naught plus the base 2 log of the square root of W times H divided by 224.
Let's break that down. W and H are the width and height of the proposed region of interest on the original image. W times H is the area. The square root converts it back to a linear 1D scalar, the approximate side length if it were a square.
And then it's divided by 224. Why 224?
224 by 224 pixels is a canonical input resolution for models pre-trained on ImageNet.
Because the ResNet backbone was initialized with ImageNet weights.
Exactly. The network's filters are natively optimized for objects that occupy roughly a 224 by 224 pixel area, so dividing by 224 normalizes the object's scale against that baseline.
Then we take the base 2 logarithm of that fraction. Because every level transition in the pyramid represents an exact factor of 2 change in spatial resolution.
And finally, K naught, which the paper defines as 4, establishing that an object with a dimension of exactly 224 pixels maps directly to level P4.
Let's run an edge case. Say the ROI is exactly 224 pixels, where root W times H is 224, divided by 224 is 1. The base 2 log of 1 is 0, so the equation is just 4 plus 0, level P4.
Perfect. Now, what about the tiny pedestrian in the background, say a side length of 56 pixels?
56 divided by 224 is 0.25. The base 2 log of 0.25 is -2, so 4 minus 2 equals 2. The tiny object is dynamically routed down to the high-resolution P2 layer,
preserving its fine-grained details before the ROI pooling quantizes it. And if it's a massive bus, say 896 pixels across, 896 divided by 224 is 4, base 2 log of 4 is 2, 4 plus 2 is 6.
But fast R-CNN only uses up to P5, so it's clipped to P5.
Right. The routing heuristic ensures the classification head always evaluates a tensor where the object occupies a relatively consistent number of spatial grid cells, absolute scale invariance.
After extracting the 7x7 pooled tensor, there's one more architectural modification. The baseline faster R-CNN with ResNet had an extremely heavy classification head.
The whole conv5 residual subnetwork, 9 separate convolutional layers on top of the conv4 features.
A massive bottleneck. But FPN naturally prevents that because the conv5 layers were already consumed to make the C5 tensor and the P5 level.
You can't reuse layers already integrated into the feature extractor, so they discarded that heavy convolutional head completely.
Replaced it with a vastly more efficient multi-layer perceptron, a 2FC MLP head.
Just 2 fully connected layers of 10, 30, 24 dimensions, followed by real U, then split into the linear layers for classification and bounding box regression.
This made inference vastly faster. Even with the extra operations to build the pyramid, FPN operated significantly faster than the single-scale ResNet 50 baseline.
Elegant architecture, but of course you need empirical validation, the MS COCO benchmark.
The ultimate test. MS COCO had 80 complex categories, heavily occluded scenes, extreme scale variance.
Much harder than Pascal VOC. And the numbers here are what made the paper legendary. On the COCO-CO test dev set, using a ResNet 101 backbone, FPN hit a 36.2 average precision, or AP.
And to give context, the 2016 COCO-CO competition winners were massively engineered ensembles. GRMI had 34.7 AP. AttractionNet at 35.7.
And FPN hit 36.2 as a single model. No iterative bounding box regression, no hard negative mining, no multi-scale testing during inference.
It just bypassed all the engineering tricks by solving the root architectural deficiency. And it ran at a blistering 6 frames per second on a single GPU.
172 milliseconds per image, the accuracy of an exhaustive image pyramid with the latency of a single-scale network.
But the real triumph was the small objects.
That's where it shines. By plugging FPN into RPN, overall average recall jumped 8.0 points. But for small objects specifically, recall was boosted by a massive 12.9 points.
12.9 points. The top-down pathway successfully forced semantic intelligence down into the P2 tensor,
enabling the RPN to confidently propose bounding boxes for tiny targets that were mathematically invisible to the baseline.
Now let's dissect the ablation studies. The researchers basically broke the model to prove why it works.
The science is in the ablations. The first one, removing the top-down pathway. They tried making predictions directly from the independent C2, C3, C4, and C5 tensors,
simulating the failed SSD methodology across the whole network.
And performance collapses. Average recall plummets from 56.3 to 49.5. Small object recall drops from 44.9 to 30.5.
The semantic gap. The deep levels are smart, the shallow levels are dumb.
C2 has immense spatial granularity, but it's just raw geometric gradients. It lacks the semantic depth to identify a dog. They even tried training independent weights for each level, hoping a dedicated head would learn higher-level semantics.
And it still failed. You can't extract semantics that don't exist in the tensor.
The top-down pathway is mathematically mandatory.
Okay, second ablation. What happens if you remove the lateral connections? You keep the top-down pyramid, but you isolate it from the bottom-up sequence.
Conceptually, it seems like it could work. You have the deep semantics from C5, and you artificially generate finer resolutions by upsampling.
But performance drops by 10 points. AP just tanks. Why?
Spatial quantization error and feature blurring. As a tensor goes through the strided convolutions of ResNet, exact pixel coordinates are subsampled and shifted. By C5, the spatial location is severely generalized.
And if you repeatedly upsample that generalized tensor using nearest neighbor interpolation, you are just magnifying the spatial error.
Enlarging a blurred coordinate. The model knows a cat is generally in that quadrant, but the bounding box is sloppy.
The lateral connections provide the exact pixel coordinates. They anchor the upsampled semantics to precise locations.
Exactly. The final ablation is evaluating the necessity of the pyramid itself. They kept the whole FPN structure, but routed every single anchor and row I exclusively to the highest resolution P2 layer.
Because P2 theoretically has everything, right? Highest spatial resolution from C2, deepest semantics from the top-down ejection. Why distribute the workload?
The AP was 33.9. Respectable, proving P2 is superior to any single tensor in a standard convnet. But it underperformed the full pyramid by about 2 points.
Because evaluating objects of vastly different scales on a single spatial grid makes the network struggle with scale variance. The hierarchy provides inherent robustness.
And the fatal flaw of the P2-only approach is computational overhead. If you process all 15 anchor scales across every spatial location of the massive P2 tensor, the network generates an unmanageable 750,000 region proposals per image.
The inference latency becomes catastrophic, so scanning across multiple pyramid levels is inherently more robust and computationally imperative.
Having validated this for bounding boxes, they wanted to prove FPN was a universal multi-scale feature extractor, so they applied it to segmentation proposals.
Instant segmentation, drawing precise binary pixel masks around the exact contours of an object, order of magnitude more difficult than bounding boxes.
And FPN adapted seamlessly. They kept the exact same P2 through P6 pyramid unmodified, just changed the prediction head to a fully convolutional pipeline.
Pushing the FPN through a simple 5x5 multi-layer perceptron to predict 14x14 masks, and adding a 7x7 MLP to handle half octaves, the intermediate scales.
The results absolutely destroyed previous state-of-the-art mask generators like DeepMask and SharpMask,
which relied on heavily, densely sampled brute force image pyramids. FPN outperformed them by 8.3 points in average recall, nearly doubling accuracy on small objects.
While running massively faster because it didn't require an image pyramid, a single forward pass through an FTN backbone provided a richer, more accurate spatial representation.
Which leads right into FPN's legacy and its blind spots. Explain how this paper permanently changed the trajectory of computer vision.
It basically became the default backbone for almost every major object detector that followed. Just months later, the FAIR team used it to engineer mask R-CNN.
And RetinaNet, Panoptic FPN, the YOLO versions, FPN became a primitive operation in computer vision.
But it's important to look at the acknowledged limitations in hindsight. What did they miss?
The blind spots. The architecture still relies heavily on heuristic anchor generation. The 32 squared to 512 squared boxes.
In the hard-coded mathematical formula to assign row-i's to pyramid levels, it forces the network to allocate resources based on rigid logic rather than letting the network dynamically learn which scale to attend to.
There's also the row-i warping issue. The row-i pooling operation is a warping-like operation that is inherently lossy. Snapping continuous bounding boxes to a discrete integer grid introduces subpixel misalignments.
Highly destructive for small objects. If a pedestrian is 10 pixels wide, shifting the grid by a fraction of a pixel obliterates the edge data. The authors noted this as a reason why using just the single finest scale, P2, wasn't fully capitalized on.
It wasn't until row-i aligned in MS COCO R-CNN that this was resolved using bilinear interpolation.
And if we contrast FPN with modern transformer-based vision models like DTTAR,
The detection transformer.
the evolution is stark. DETR removes the need for anchors and heuristic scaling entirely. Attention mechanisms handle scale variance natively. Cross-attention allows the model to dynamically attend to any spatial location across the whole image scale based on learned relevance.
Bypassing the rigid constraints of a pyramidal hierarchy. But FPN was the absolute apex of convolutional routing, the vital bridge to today's dynamic attention models.
A foundational text.
Which perfectly transitions us to our novel notion segment. Now for our novel notion segment, where we pitch outlandish but logically plausible new research ideas inspired by the paper's legacy. A quick disclaimer. This segment is for entertainment purposes only and explores extreme theoretical scenarios.
And routing topology is highly adaptable. What's your first pitch?
Idea 1. Temporal feature pyramids for predictive video generation. If we look at AI video generation models, like Sora, they excel at frame-by-frame physics, but they suffer from severe long-term hallucinations. Objects morph, the narrative completely disintegrates over 10 seconds.
High temporal resolution, low temporal semantics. So how does a temporal FPN resolve this?
We transpose the spatial pyramid into a temporal pyramid, build a temporal FPN. The bottom-up pathway analyzes frame-by-frame physics at 30 FPS, high temporal resolution, low semantic prediction.
And the top-down pathway operates on a heavily subsample timeline.
Exactly. The C5 equivalent evaluates keyframes spaced 5 seconds apart, low temporal resolution, high semantics, like knowing a car is going to crash 5 seconds from now.
And the lateral connections?
We use them to inject the future narrative into the present physics rendering. We temporally upsample that 5-second collision prediction, apply a 1-by-1 temporal convolution, and merge it via element-wise addition into the 30 FTS pathway.
So you mathematically force the short-term physics renderer to be constrained by the long-term semantic narrative. The model can't hallucinate a morphing car because the top-down pathway is injecting the collision state into every intermediate frame.
Exactly. Constraining hallucinations. What's your extrapolation?
Idea 2. Pyramidal lateral connections for infinite context LLMs. Applying the FPN routing trick to large language models to solve the long context window problem.
Bypassing the quadratic scaling cost of standard attention over 1 million tokens.
Right. Instead of processing a massive book linearly, we build a linguistic feature pyramid. P2 operates at the token level. Localized grammar, immediate syntax. P3 at the sentence level. P4 at the paragraph. P5 at the chapter level.
So P5 is highly semantic, broad context.
And to route that intelligence down, we conceptually use nearest neighbor upsampling to project chapter-level semantic embeddings down onto the token-level processing, fused with a 1-by-1 linear layer and element-wise addition.
Injecting the macro narrative directly into the microsyntax layer. It allows the LLM to maintain perfect global context while predicting the next specific token without calculating a massive attention matrix across the entire document.
Semantic abstraction and fine-grained resolution are inherently antagonistic forces. Multi-scale routing via lateral connections reconciles them.
I love that. Which leaves us with a final, provocative thought about the nature of perception. FPN proved that looking at the world isn't just about zooming in. It's about projecting your high-level understanding of reality back down onto the raw, granular pixels of your immediate vision.
Does human cognition use its own top-down lateral connections?
Exactly. When you glance at a crowded street and instantly recognize a friend, is your visual cortex relying solely on a bottom-up scan? Or is your brain's semantic executive suite actively hallucinating a top-down projection, using your contextual expectation to force the raw optical signals into a recognizable bounding box before you're even consciously aware of it?
True vision is a two-way street.
Thank you for joining Talk Tensors. We encourage you to look at the world at multiple scales today. Until next time.